Okay, so I gave this quiz because it's been a while since I gave a quiz where you actually had to show me that you did and understood your homework, right? And you had to do it on your own. So I felt it was an appropriate time because I don't want everyone getting complacent. I know Thanksgiving is right around the corner and everyone can see the finish line, but we still have a lot to do, all right? So you need to stay on top of everything. Let me see, 3 raised to the x squared minus 7 equals 27 to the 2x. So when we're asked to solve this, what we did last class, we tried to figure out if there was a way that we could rewrite the bases as the same number. You all remember that? So we recognize hopefully that 27 is 3 cubed. And so we can rewrite this as 3 to the x squared minus 7 equals 27, which is 3 cubed to the 2x. And then what do we do? The 3 times the 2x using a property of exponents. So this becomes 3 to the x squared minus 7 equals 3 to the 6x. And since these both have the same base now, you just need to get the exponents to match, right? Make those equal to each other. So you let x squared minus 7 be equal to 6x, and that's a quadratic equation. And you move everything to one side, put it in descending order. That way you can factor it. And that's a pretty easy one to factor. Plus 1 and minus 7. So your two solutions, -1 and positive 7. Okay? So this is what I'm looking for. I'm looking for this work. I'm not looking for you to sit there on your calculator and try and get your calculator to come up with the two numbers, like checking and trying to figure out what happens. Okay? It's the technique that's important here. Any questions now that I've gone through it? Okay. All right, let's start with today's stuff. Last time we talked about exponential functions and solving exponential equations. And today we pick up in the next section, 6.4, logarithmic functions. This is the last type of function we're going to study in this class, so that's good news. So let me try and motivate this by putting something on the board, all right? Just to get us to think about it. If I write this down, tell me if you agree with this or not. 4 squared is 16. Everyone agrees with that? Yes? Now let me write something else down. If I write 4 to the x equals 16, you can just look at that and tell me what the answer is without having to do much work, right? Everyone agree? You just, 4 squared is 16. We all just kind of knew that. But if I'm trying to explain this to somebody, how would I tell them what I'm looking for here? Like in words, I would say something like, I'm trying to figure out what power I raise 4 to in order to get 16, right? That's what I'm saying? What power do I raise 4 to in order to get 16? 2, right? But me asking the question, that's how I have to say it. And so what we do is we come up with another way of writing this so that it's understood that everything I said in words is translated into a symbol. I don't know if this can make sense until I write it down. So let me just convert this into this expression. Sorry. All right. So this is brand new notation. So what the heck does this mean? Well, first let me tell you how you would say this if you were talking. You would say something like log base 4 of 16 equals x. That's the way you say that. Log, or logarithm, but we'll say log for short. Log base 4 of 16 equals x. I have heard some people say log of 16 base 4 equals x, but this is the way I'm going to do it because it's kind of like left to right. Log base 4, 16 equals x. This equation and this equation are equivalent. They're the same. They're asking you for the same thing. It's just a different way of writing it. All right? So this is purely from here to here and back and forth. This is purely notation. That's all it is. It's just notation. If I want to ask you to tell me what power I raise 4 to in order to get 16, this is the same exact question. So look, imagine the x isn't there. This right here is enough for you to see that it's the same question as this one. See, what power do I raise 4 to get 16? That's what's being said here. The log is what tells you you're dealing with powers here. Understand? So you tell me right now, if I write something here on the board, what question it's asking. If I write, as an example, log base 5, 25. What's that asking? Don't tell me what the answer is, just tell me what it's asking me. Go ahead.
To what power is 5 equal 25?
To what power do I raise 5 in order to equal 25, right? Or 5 raised to what power is 25? Do we all know the answer? What is it? 2, right? 2. So the answer to this should be 2. Let me write another one down. Log base 7 of 1 over 49. So first of all, translate what that's saying. What is it asking you to do? 7 to what power is 1 over 49, right? That one might not be as obvious. It might be obvious. It just depends on you and the way your brain works. So let me translate this to the equation, all right? This right here, let's say that this is equal to x, right? And we want to know what that is. Translating this means 7 to the x is 1 over 49, right? That's what that means. Does everyone see this is just another way of writing something we've already done? Okay. Very important that you see it's just switching back and like we can switch back and forth. Anyone know what that power should be? -2. -2. So you could do it. You could rewrite this as 1 over 7 squared. Bring the 7 squared up. It'd be -2, and you match the powers. Let me give you another one. Log base 4 of 1. What's the question being asked? To what power do I raise 4 in order to get 1? 0. 0, right? In fact, if I do log base 2, 1, what would the answer to that be? 0. Log base 13, 1. What would that be? 0. Would you agree that no matter what base I use, if I put a 1 here, I'm going to get 0 every single time? Because the only way you can get 0 out is if you raise the number to, the only way you can get 1 out is if you raise the number to 0, right? Except for 0, right? So I'm glad you brought that up, because there are some issues we had when it came to raising things to powers. We always wanted to make sure that power was, or that power when we were raising them was what? Greater than 0, but never 1. Remember we tried to avoid that? Okay. So we're going to have the same sort of restrictions here. I haven't stated that. Right now I'm just kind of getting the idea of what a logarithm is first. All right, so let me kind of summarize this, all right? Trying to dry that towel out a little bit. In summary, if somebody gives you a to the x equals y, we can write that in a different way. What would it be? Log base a of y equals x. Do you agree that that's really what's been happening here? Okay. Now, whenever we were dealing with this left side, see this left side? Isn't that an exponential function? Yes? So we had restrictions. Here the restriction was that a had to be greater than 0. A could not equal 1. And so we're going to have the exact same restrictions over here. A has to be greater than 0. A cannot be equal to 1. I'm sorry?
You want us to always state that?
Always, one is always what?
You want us to always state that?
No, you don't need to state it. Just remember that you can never have a base of a log be a negative number, and it can never be 1. And it can't be 0 either. You can't have a 0 base log. So whenever somebody writes something down like this, where you have a base and an exponent, right, in the equation, this is called exponential form. And this over here is called logarithmic form. We said we can go back and forth, right? If someone gives us this, well, if someone gives us this, that really it meant this, right? And it goes the other way around. If someone gives us this, it really means this. So it's it's the same idea written two different ways. And so it's exponential form and logarithmic form. Understand? Okay. So I'm going to point something out. Another thing that I think is very important is that if you're trying to go from exponential form over to log form, what will the base of your log always be? The base of the exponential, right? So the bases will always be the same thing. But the exponent here actually becomes the other side of the equation. And the other side of the equation here becomes what's inside the log here. Understand? You'll see that kind of switch a little bit. Also, the x up here was up in the exponent. In the log form, isn't it actually pulled down? And remember we were looking at some problems where it would be like, where we were saying it would be real nice if the x wasn't up there. It would be nice to have it down instead. This is actually what we're going to do to get things down out of exponents. We're going to use the switching to log form to do it. Okay, let me put a couple of other examples up here for us to just practice the switching back and forth. Let's just practice that first. So first of all, I want you to write in log form. Part A. 3 to the m plus 2 equals k. Notice I'm not asking you to solve for anything, right? I'm just asking you to convert this from one form to the other. What form is this given to us in? Or given to us? Given? Given to us in. That's what I said. All right. It's an exponential form. How can you tell? It's got an exponent, right? So we're going to convert this to log form. We said that we'll have log, and what will the base always be? The same as the base over here. 3, and then what's going to go in the log? The k, and then the other side of the equation, m plus 2. This is log form. This is exponential form. All right? So check this out. If you were trying to solve for m here, and you couldn't figure out what m was, wouldn't you actually have m over here? Like there's m, and you could actually just subtract 2, and you could try and figure out what m is? Okay, we'll get, as long as you knew what k was, right? Okay, how about this one? How about w to the y equals z minus 1. So write that in log form. So log base, what? W. What goes in the log? Z minus 1. And then equals y. Now we have to be kind of careful here because isn't the z minus 1 kind of like an entire quantity, so I need to put it in parentheses, all right? It's like if I write this, log base 4 of 16 plus 8. What do I mean here? Do I mean 4 to what power is 16? 2, do I mean 2 plus 8? Or do I mean 4 to what power is what? 24. Which one do I mean? You see what I'm saying? So the parentheses are very important. The parentheses mean you're looking at the whole thing and saying 4 to what power is that? So same with this z minus 1. W to what power is the entire thing z minus 1? So put it in parentheses. Questions? All right? Sure? Okay. Now let's go the other way. Let's go and do writing it in exponential form. So as an example, log base 7 of m equals x plus 1. Well, we said something's always going to stay the same in both forms, right? The base is always going to be the base of the log, and it's going to be the base on the other side in the exponential form. So I should have what here? 7 raised to what, though? The x plus 1, not the m, right? The x plus 1, and that must equal m. Make sense? Now, I'm going to show you something. The books don't talk about this, and I don't know, when I was a student, I was learning logs and stuff. This just made the most sense to me, and so I've shown it to my students. A way to remember to get logarithmic equations or expressions converted over to exponential form is this thing that I call the loop, okay? The loop. I just didn't have another better word for it, okay? The loop. So what I do is anytime I have a log equation, I draw a loop that goes from the 7 to the other side like this and back in. See this little loop? And this is what I raise, and this is my equal sign. So what happens is anytime you have a log equation, a quick way to get it to exponential form is you take the base, right? You go 7 raised to this equals this. 7 raised to the x plus 1 equals m. Do y'all see it? Okay. I'll be using that throughout the rest of the class. Yes? This is what you were trying to say? Yeah. So they showed you something like that also? Okay, good. Okay, how about this? Log base z plus 1 of k equals p squared minus 4. Write that in exponential form. So I'm going to come in, I'm going to do that little loopy thing now. Should be the base raised to this equals that, right? So my base is actually what? Z plus 1. Should I put in parentheses then? Yes. Raise it to the p squared minus 4 and make that equal to k. All right? So let's just make sure we're all clear on a few things here, unless there are any questions. A logarithm is basically another way of writing an exponential, right? That's all it is. It's a different notation. And anytime we have an exponential equation, we can convert it to log form. If we have a log form, we can convert it to exponential form. Yes? All right. Now let's look at some special logs. And I think this is where things start getting a little confusing. I don't know why, but it just happens. 2 special logs. All right, so let's start out with the first one, the base 10 log. I'll call this A, capital A. The base 10 log. So there are two special logs in mathematics. One of them is the base 10 log, and we'll talk about the next one in a second. So this is any log that has as its base 10. All right? And I could put in here x. Anything I want, right? So if I gave you a number, like let's say I let x be 100, this would be 10 to what power is 100, right? If I put 1,000 in here, it'd be 10 to what power is 1,000. Yes? All right, so this base 10 log is used a lot. It's used a lot in physics and chemistry, and if you've done pH scales in chemistry, it's all base 10 logs. All right? Yeah. Y'all seen this before? So base 10 is very important to us. Why is base 10 such an important thing to us? Because our number system is base 10, right? Computers are binary. We talked about that last time. It was base 2. But our number system is base 10, right? All the numbers that we ever can write come from 10 different digits, don't they? Those are the only 10 digits you're ever allowed to use to write down any number, right? There are 10 different numbers. They all represent different things. Base 10, right? If all you were ever allowed to use was 0 and 1, then you would be in binary. That would be base 2. If you're only allowed to use 0, 1, and 2, you would be in base 3. 0, 1, 2, 3, 4. Get it? I mean, it just keeps going up. Base 10 is what we use. We use it because I think it's because we have 10 fingers. Like if we had 8 fingers, we'd probably be in a base 8 number system, most likely, because we'd count everything and we'd only have 1, 2, 3, 4, 5, 6, 7, 8. So we'd have 0 through 7 probably instead. Anyway, okay. But we are in base 10, so we use it all the time. And so what they decided, and when I say they, I don't know who that is. Some people before us decided that anytime we see this, we're not going to write the base 10. We're just going to write log. Now, it's kind of like this. Do we all know the difference between this and this and this? What is this? Square root of 2. This is cube root and fourth root. So I wrote 3 here to let you know it was cube root, 4 to make sure you knew it was fourth root. I didn't write 2 here to make sure you knew it was square root, right? But it was understood. We all understand it's a 2. We all understand without writing it that that's a 2. Same thing here. If you don't write the base, it's understood to be a 10. So it's really hidden here as a 10. Understand? Now, I didn't like that when I was a student because I was like, well, why do that? I mean, why just write the freaking 10? It's no big deal, right? I mean, write the 10. So why do that? And actually, there's a pretty good historical answer for this. If you think back before word processors, before computers, if you ever had to put together a paper, like if you were studying something in chemistry, you might have to write log base 10 in your paper. Maybe you have like a 400-page paper that you're writing, and maybe you have to write log base 10 in that paper 1,000 times. It's some research you're doing, right? Then when typewriters came out, I don't know if anyone has ever used a typewriter. Anyone ever used a typewriter? Okay, have you ever tried to subscript on a typewriter?
No.
Okay, so typewriter, you type, the letters actually strike the paper, right? And when you want to do a subscript, you actually have to take the drum and do like a little half rotation, and then type 10, and then go back and then keep writing. And if you had to do that 1,000 times, it would be a real pain in the ass, right? So what they did is they said, just don't write the 10, we all understand it's 10. And then they could type without ever having to stop and do your little drum rotation. Understand? If you had to do something else, of course. But that's why we use other notation too. We try and shorten it. So that's what I've heard is the historical reason behind it. It's used so much we just got rid of the 10. It's all understood to be 10. All right? So let me ask you this question then. What is this? I'll ask you a few questions. What's log 1? What is it? 0. We said that already, right? Anytime you plug 1 in, anytime this is a 1, no matter what the base is, this is going to be 0, isn't it? All right. Now, I'm going to verify that real quick. Check this out. If I write down what this actually means, it means log base 10 of 1 equals 0. Couldn't I verify that mentally real quick with the loop? 10 raised to the 0 needs to be 1, is it?
Yes.
Yes. Right? Okay. How about this? What's log of... I'll go a little harder since I think I'm... log of 0.01. What do y'all think? Let's try and rewrite it with the red. Can we do that? Can we rewrite it with the red? We rewrite it with red. This really means log base what? 10. And then isn't 0.01 the same as, remember the positions here, 1/10? These are our tenths. These are our what? Hundredths. Ooh, hundredths. So isn't this 1/100th? So I can put this as 1 over 100. And then if I'm saying what is this, right, I could call this side anything I want, call it x, and then draw your little loop. And this becomes, what, 10 to the x is 1 over 100. Now can you get it? What is it? -2. Because we did this a couple of times last class, right? This is 100 is 10 squared. 1 over 10 squared is 10 to the -2. You match up the two tops, x is -2. Y'all see it? Okay. That quiz made it quiet. And you know what? Nathan's not here. That's what it is.
And neither is in here.
You know what? Yeah, it is kind of tranquil in here, isn't it? We miss them, right? We miss them? All right. Okay, so that's one of the special logs. Anytime you see LOG, that's going to be log, base 10, right? I'll give you one more example. I know, damn it. What's log 4? Right? So what is the question that this is asking you? 10 raised to what power is 4, right? Are you going to be able to get that? No. However, get your calculators out, because I asked you to bring them, right? From here on out, I asked you to bring them. This is your last warning day for the calculator. From this point on, right? From this point on, if you don't have your calculator, I'll count it as a 0 on a quiz grade. Everyone else will get 100. Okay? We understand? It's on video. All right. So if you look on your calculator, do you see an LOG key? Has to be LOG. Yeah? Try and use your calculator to figure out what log 4 is. You got? 0.60 something? So according to the calculator, 0.6, go ahead.
0.60205 999
999 13. Okay, so your calculator is going way out here, right? And we don't need to go that far right now, but let's just, as long as you're getting like 0.60205, something like that, the first 4 or so digits, we're good? Okay, if you're not finding that on your calculator, let me know, all right? And I can help you. So we have a key to take care of the base 10. We can do base 10 logs for anything, can't we? According to, if your calculator has a key, we should be able to do it, right? Good. All right, so we'll never get hung up on base 10 logs. Never. All right, so that's the first special log. The second special log, anybody have a guess as to what it is? What base it is? Log base E. It's the log base E of x. Now this is tied into, remember when we were studying exponential functions? There was a very special exponential function that we called e to the x. And I made you get your calculator out and we graphed it and everything else. We said e was this number, it was approximately 2.718, something like that, right? I told you it's very important, it's used, hopefully in calculus they'll show you why it's so important, right? So if we use this number as a base in a log, then it's a very special log. So everyone understand that the base of this log is approximately 2.718 something. Yes? And again, it came up so much that they didn't want to have to write the E over and over and over and over. And if they were typing, they didn't want to have to use the drum rotating and stopping. So what they did is they said, we need to have a shorter way of writing it. They can't use log, L-O-G, because we already used it for 10, right? So they wrote ln. This is an L, lowercase l. I always write my n's that look like capitals always. So you could write like that, ln of x. And it's called the natural log. And I believe if you were to try and say natural log in French, are there any French-speaking people in here? Yes, a little bit? No? Okay.
I don't know how to speak French.
Okay, but that sounded pretty convincing. All right. So, but what do the French do with things like this when they say it? Wouldn't they do like the logarithmic and natural? Like they wouldn't say natural log. They'd say like logarithmic, whatever, natural. That sound like French to you? They reverse it, right? L before the N would be the way they do it. And that's where it's coming from. The L comes before the N. This is the logarithm natural. Got it? Which we call the natural log, right? And we call it also the natural log because the E I told you was called the natural exponential function because it's the only function that behaved that way. It just kind of naturally occurred. We don't know why it works, but it just does. All right? All right, so with that, we can ask more questions like, what is natural logarithm, whatever? I'm kidding, of 1. What is that? 0. Okay, don't let me get you, ever on something like that. 1 inside of a natural log, that's always going to be 0. How about natural log of 5? So what is the question this is asking?
E to the x.
E to what power is 5? That's what this means, right? See how I'm converting this over? I'm like saying, hey, this is something, I don't know what it is, and I'm switching it to exponential form. Does anyone know what you raise e to get 5? No? Does your calculator know? Yeah. You actually have a natural log key on your calculator. So you can just do the natural log of 5 on your calculator.
1.60. Does it matter if the parentheses are on?
Yes, it will. But see if you get what? 1
1.6094.
Good enough. 94. That's good. Does the answer seem reasonable to you? E raised to that number. Remember, E is almost 3, isn't it? If you take 3 and raise it to a number bigger than 1, it should be bigger than 3. It needs to be 5. So, all right, we good? All right, so we have, again, trying to keep track of everything. A logarithm is just another way of writing an exponential. You can convert back and forth between the forms. There's 2 very special logs, the base 10 log and the natural log, and we have some slight adjustments that we make to the notation whenever we use those 2, right? All right. So now we're actually going to come up with a function. So with all of this said, we define what's called the logarithmic function with base A. Here it is. I'm going to define a function, f of x, and say it's equal to log base A of x, where A is a positive number and A is not equal to 1. So just like every other function that we've studied, you plug something in, it spits something out, right? The thing I'm going to plug in here is this x. And so when I plug it in, every single number I plug in there, I'm going to be saying to myself, a to what power is that number? A to what power is that number? A to what power is that number? Over and over and over, I'm going to be asking myself that question. And every time I get an answer, then I'm going to be able to plot points on a graph. So let's take a look at a specific example of a logarithmic function. That's what every logarithmic function looks like, but here's a specific example. F of x equals log base 2 of x. This is the base 2 logarithmic function, right? The a here tells us what the base is. This is base 2 logarithmic function. I'd like for us to actually sketch it, draw it. Give me a picture. Are you ready? Do you remember how we sketched exponential functions? We did a t-chart, right? T-table. We're going to do, I guess for our first example, we're going to do a t-chart just to see how the t-chart is a little difficult for logs. You'll see. So if I just come in here and I say here's x and here's the y value, which is f of x. If you go back to last class, when we did the exponentials, we just plugged in like 1, 2, well 0, 1, 2, and 3, and then we did like -1, -2, -3, and we were done. Here, it's not so easy. Let's see if we can tell why. Let's try to plug 0 in. Try to plug 0 in. And I'm going to put the 0 in red because I want you to see what kind of trouble we're going to get into. Try and plug 0 in. What's the question we're asking here? If I plug 0 in to that, it's log base 2 of 0. What's the question that this is asking? 2 raised to what power is 0? Isn't that the question it's asking? 2 raised to what power is 0? Nothing. That's not possible. Now, look at that left side. What is 2 to the x? If I asked you to graph it, what is 2 to the x? That's last class. 2 raised to the x.
1, 2, 4.
What type of function is 2 to the x? Exponential. And do you remember what this graph would look like? It grew, right? It was exponential growth like this. And we said it had a horizontal asymptote. Do you remember this? That's what 2 to the x looked like. Can that ever be equal to 0? So does this ever hit the x-axis? Absolutely not. So this is actually, there's undefined. I can't plug 0 in. So that sucks because that means I have to be careful what I plug in, right? Let's try 1 this time. I'll put it in black because it's going to work. If I plug in 1, what happens? I get log base 2 of 1. And what do we say? Anytime you put a 1 into any log, you get 0, don't you? So I'm going to get 0 here. Oh, good. All right. That wasn't bad. How about 2? That's saying log base 2 of 2. So the question is, 2 to what power is 2? 1, right? So this is 1. That wasn't bad. He said it was going to be bad. All right. How about 3? Why is it in red? 2 to what power is 3? Right? That's the question? 2 to what power is 3? Not happening. Can you use your calculator? What's the base of this log? 2. Your calculator can only handle what? Base 10 and base e. That's it. What's that? Okay, so I'm not there yet. We will be able to get around that. Because the next natural question would be, well, why in the hell doesn't my calculator have the ability to do all logs, right? Why does it only have 2 keys? And it turns out we have something called the change of base formula. You'll get that at the end of class today or the beginning of next class. Okay?
If I'm not mistaken, there is a calculator that has it working.
Yes, there is. There is some, and it's a more basic calculator, too. It's not one of the fancy ones.
I think the 82.
Yeah. One of them has it. It's a thin one. The thing about that is, although I like that feature, someone who understands the mathematics understands you really only need 1 log key to do all logs. So although it's cool, it really kind of prevents a person from knowing how logs really work, I guess. All right, so this one, though, we can't do, right? 2 to what power is 3 not happening today, right? Okay, so this, it's not undefined, I just don't know what the hell it is, right? It's a difference. 0 is undefined, this is a question. So that means I have to be careful. When I plug a number in here, I'm going to need to know the answer. So the numbers I plug in here should be powers of 2, shouldn't they? Because I know what the powers of 2 are. So what should the next number be that I plug in? 4, right? That way I'm asking myself the question, 2 to what power is 4? What is it? 2? What's the next number I should plug into this T-chart? 8. Why not 6? 6 isn't a power of 2, right? So I should plug 8 in next. Do y'all understand what's going on here? I'm plugging in 8 next. And that's telling me log base 2 of 8. And we know that that's 3 because 2 cubed is 8. 2 to the third power is 8. So 3. What's the next number I should plug in there? 16 would be the next power of 2. 16, and what should it spit out? 4. And I could keep going. Next one I would plug in would be 32. We get 5, 64, right? And keep going like that. So I think we have a kind of an idea of what's happening on that side with positive numbers. Let's try a negative number. How about negative 1? Oh, I better do that in red. Why is negative 1 going to be red? Yep, that's right, because when we're saying this, right, we're saying 2 to what power is negative 1? Go back to that graph of 2 to the x. Can this ever be negative?
No.
It couldn't even be 0, right? So it's never going to be negative. So this is not going to happen, undefined. Oop. Pardon? Unless you move it down, right? Is that what you're going to say?
Can it be negative, like a negative wall?
Down here?
No, like down to 1 something. Yes.
Yes, but that would be if we put a negative in front of the log. Yes, then it could. I'm saying for this particular problem, it couldn't happen. So undefined, yeah? And in fact, any negative number, right? A negative number doesn't matter. It's going to be undefined. All right. So it looks like if we were to graph this so far, let's do it. Let's go ahead and graph this as of right now. Let's graph it. Here's where we are. Okay, if I were to graph this, I know that I cannot draw from 0 over, can I? Right? So far? Because every time I try and plug a negative number in, nothing happened. When I plugged in 1, what did I get? 0. When I plugged in 2, what did I get? 1. When I plugged in 4, what did I get? 2. The next one I plugged in was 8. When I plugged in 8, I got 3. So this graph appears to be growing, doesn't it? Yes? I mean, it's slow growth though, isn't it? I mean, it is growing, but it's not that fast. The next one would be 16, and then I'd go up another one. Then 32, I'd go up another one. And then 64, another one, 128, 256. So it takes a while for this growth to happen. So it's not like exponential growth, is it? Doesn't look like it. We know we can't plug in 0 because it's undefined. We know we can't plug in any negatives. What have we not looked at then? What should we look at that's not been addressed yet? I mean, I know it does this, right? I know it goes like this. I know that from 0 over, it's undefined. How about something in here? What does it do as I get closer to 0? What does it look like it's going to do? Looks like it's maybe going to dive down like this. Let's see. What would be a good number in here? How about 1/2? What would happen at 1/2? So you'd be doing log base 2 of 1/2. Yeah, and then that would be 2 to what power is 1/2? And that would be -1. Does everyone follow that from last class? What should the next number I pick be if I'm smart about this? 1/4, right? If I pick 1/4, then I'm doing log base 2 of 1/4, which is -2. Again, this is from last class. 2 to what power is 1/4? 2 to the -2. Are you following?
Yes.
Okay. What would the next number I pick be? 1/8, and then 1/16, and then 1/32. And what happens is each time it's -1, then -2, then -3, right? And each time? So at 1/2, I was at -1. At 1/4, I was at -2. Now I can't go in, I can't zoom in anymore, but if I went to 1/8, I would be down even further. If I went to 1/16, down even further. 1/32, down even further. 1/64, down even further. And can I just keep on getting closer and closer without ever actually getting there? Right? I could, right? And so what's happening is it's diving down like this. And so what I have now is a vertical asymptote. You all see it? Okay. So I'm going to put something up here for us. For y equals log base 2 of x, we had a bunch of points on here. I'm going to just put them on here so we have them kind of summarized. We had 1, 0. We had 2, 1. We had 4, 2. We had 8, 3. We had 1/2, -1. We had 1/4, -2. And 1/8, -3. Do you agree that those are the ordered pairs of the log function base 2? Yeah? Now, I want you to go back, and if you want, you can look at your notes, because it should be in there if you take notes. I want you to go back and look at the function 2 to the x. Not log base 2 of x, but 2 to the x. And if you look at when we did this in class last time, we created a t-table, and we had in that t-table the point 0, 1. We had the point 1, 2. We had the point 2, 4. We had the point 3, 8. And then when we did some negative numbers, we had -1, 1/2. We had -2, 1/4. And we had -3, 1/8. Do y'all see that? Anyone who took notes, is that in there, the table? And do you see the similarity between those? What are they? They're just flipped, right? And what did we say in class when we were talking about inverse functions? We said every time a function first, this function would what? Send 1 to 0, and this one sends what? 0 back to 1. Or you could say this one sends 0 to 1, and then this one would send that 1 back to 0. So no matter how you do it, you go this way or this way, these two functions undo each other, which means that they are inverses. Understand that? So if I graph the blue one, which is 2 to the x, and let me label this. This is y equals log base 2 of x. If I graph 2 to the x with this one, at 0 we were at 1, at 1 we were at 2, 2 we were at 4, 3 we're at 8. It would look like this. Yes, this is going to look like that requirement that we needed. So you see those two? That's 2 to the x. And if I draw the diagonal in here, like this, you can see that they are mirror images of each other over that diagonal. Therefore, they are inverses of each other. Okay? So what would be a more efficient way of graphing log base 2 of x? What would be the most efficient way, if I asked you, starting this whole problem over, knowing what we know now, what would be the most efficient way to graph this? Yeah, do this, because this was easy, right? Plugging 0 into here, plugging 1 into here, 2 into here, 3 into here. We didn't have to worry about picking these numbers smart, did we? Here we have to worry about how we pick them. But if we just pick numbers like this, take those answers, flip them over, then we would draw the black one, wouldn't we? That's the most efficient way to graph the log. Got it? Okay. So you start with the exponential, and then you flip the ordered pairs. So let's talk about some properties of the log functions. So if somebody gives you a log base A function, what are some properties in terms of the way it looks? Liz, you look bored again. So you want to help me out here, Liz? Huh? I know, I'm going to ask you to help me with this. With the log base A function, what point will it always have in it? 1? 1, 0, right? 1, 0. If I plug in 1, I should always get 0. We knew that for any log, right? And if you look at the exponential functions, back from last class, we had this happening or this happening. Oh, whoa, like that, right? And it always had that point in there, 0, 1, didn't it? For an exponential? So if the log is the inverse, then if we flip that ordered pair, it should always have the point 1, 0, shouldn't it? So this point will always be in every log function. Then the right side's going to go like this and grow slowly. And then to the left, it's going to dive down and have a vertical asymptote instead of a horizontal asymptote. So this is what I was going to ask you, Liz. What's the domain of all log functions then? Yep. What's the domain here? Parentheses 0 to infinity. Good. So the graph exists from 0 to the right, but not at 0 because at 0 you have the vertical asymptote. All right. Anyone else? What's the range? Everything from the bottom all the way up through the top, isn't it? You can go as far down as you want. There's going to be red graph somewhere down there. And you can go up as high as you want. Somewhere out there is that curve is going to catch up to it eventually. So the range is negative infinity to infinity. All right, good luck. Today's the day. All right, so remember on this exponential functions, what the domain was over here? What was the domain? What was the range? All real numbers. And the range over here was 0 to infinity. What has taken place here? They switched, right? They switched places, which makes sense if you look at the picture of the way inverse functions work. Whatever comes out of this is what goes into this one, and whatever comes out of this is what goes into that one. It's the domains and the ranges switch places with inverse functions.
With every inverse function?
Yes. All right. Now, I wonder if there's a way we could change it. Like over with this, we were able to do something. This is always going to hold as long as the A here, I should probably put this above here. This is the graph if A is bigger than 1. The graph of log looks like this if A is bigger than 1. Which one of these was A bigger than 1? Which one? Was it 1 or 2? A bigger than 1. It was 2, right? Exponential growth happens when A is bigger than 1. Exponential decay happened when A was less than 1, wasn't it? So what is it going to look like over here if I let A be less than 1 for a log? It has to still have this point, right? It's going to go like this instead. This is what happens for a log if the A is less than 1. And of course, A has to be greater than 0 or else it's not a log. Go back and look into your notes from last class. There were 2 different types of exponential functions we could have depending on what the base was. Well, we have the same thing with the logs. The log will look like this red one if the base is bigger than 1. The log will look like this black one if the base is like, let's say, 1/2. Yes, we have what would be considered to be logarithmic growth and logarithmic decay, but it's not the same as exponential, because exponential is usually much faster, much more rapid growth. But it's still growing. All right, y'all doing all right? Let's do one example of a graph, okay? How we could sketch something. Let's sketch f of x equals negative log base 3 of x minus 1 plus 2. All right, this problem we're going to put it all together, all right? We're going to put everything we've done today in the last class together into one little problem here where we're going to sketch. This is a good example of a test problem. Sketch that. So you look at it, the first thing you notice, hopefully, is that it's a log function, right? And your base is what? 3. So I said if you want to graph a log function, you should probably save yourself some time, and instead of looking at a t-table for this, go look at a t-table for what? The exponential version of this, which would be 3 to the x, wouldn't it? Don't worry about all the reflecting and shifting and all that crap. Don't worry about that yet, all right? Let's just go look at a totally different function, which would be the function f of x equals 3 raised to the x. Make a t-table for this one. A t-table for this one. The common numbers that I like to use are 0, 1, 2, 3, -1, -2, -3. That should be enough to get us a good feel for what this thing looks like.
Why just 3x instead of making that?
Don't worry about all that, okay? Because what this is, it's the inverse of 3 to the x moved around. That's all it is. So that's what we're going to do. We're going to figure out what the inverse is and then move it around. So we plug in 0, we get 1. We plug in 1, we get 3. 2, we get 9. 27. 1/3, 1/9, 1/27. Right? Those are going to be the numbers if we plug them in. We aren't interested in that one, are we? No. We're interested in this one flipped over, right? All these order pairs flipped over. So what I'm going to say is this. Not this function, but the log function. Y equals log base 3 of x, without all of the -1 plus 2 and the negative out there, without all of that, is just these points flipped over, isn't it? So I'm going to write those down. That is going to be 1, 0, 3, 1, 9, 2. I think that's, I won't use the 27, 3 because my graph's not going to be that big. 1/3, -1, 1/9, -2. And again, I won't use the 1/27th. Well, I could do that one. 1/27th, -3. We good? Just flipped all those over? Let's plot those. And we'll get a rough idea of what this log function looks like. With me? One, 0. There. 3, 1 is here. 9, 2. So 4, 5, 6, 7, 8, 9, and 2 is there. So I know it does this. And then I know it dives down like that.